This study comes from the infant cognition lab, so they're studying humans, but seeing how infants think. And so they do these really interesting studies on infants that can't speak, but they're still able to see what they prefer, and they do all kinds of creative things. So this activity is based around a study that they did at Yale at the Infant Cognition Lab. So I want to show you a video that kind of, you can just see. So they got some pre-verbal children. These are how young they are. Kind of cute. And they showed them these two things. All right, so I'm just going to play it. Okay. All right. So my question for you is, make sure your names are on this. Do you know the names of the people in your group? Go ahead and write the names of all the people in your group on your piece of paper. And then I would like for you to answer part A. All right, y'all, let's report out and see what folks had to say. Okay, so the question was, what? Of 16 pre-verbal children who participated in the study, whoops, typo, how many do you think chose the helper toy? Why? What factors do you think might be at play when the children made their choice? Okay. So, Jackie. Okay. Right, so 50%, which in this case would be how many? 8. Okay, 8 kids. Okay, so let's see, maybe some people agree. Maybe some people, was your whole group in agreement, or did you have any dissenters? I heard as I was roaming around, they're just little kids. What do they know yet? They don't know anything yet.
We don't, I'll just give them a
Yeah, okay.
guess. Prefer the broader color.
Okay. So maybe color preference.
Or dominant hand, favorite left-handed or right-handed
Okay. Dominant hand. Did anybody else have thoughts like this? That maybe there's a design in the study? What did you all say? Color preference. What about the shape itself? Did anyone say? Maybe they like, I thought I heard you all saying triangles, right? Maybe they like the triangle. Triangles are fun and happy. So color. If the researchers were carefully designing the study, then what should they, so that they didn't want color preference and shape preference to bias, because you all were talking about statisticians valuing, like, not being biased. What could they do to control for color, shape, and,
They could switch which sides the triangle and square were on, and then they could also switch which colors each of them were.
So if they switched it up every time, then that would control for that. In fact, yeah, go ahead.
Or they could use
back off with the same shape. So as long as they randomized it and another thought that I had was, what if one of the toys was closer to the child when they presented it to the child, right? So they would want to make sure that there was a center line and that they were both the same distance away. What about if the child's just like grabbing for stuff, right? Did it look like this child made a choice? I think so. So that's another thing that they would probably want to make sure. Now, so these researchers did account for this. So sometimes the helper toy was a circle, sometimes it was a square, sometimes it was pink, sometimes it was blue, sometimes it was yellow, and so on. Sometimes it was on the right, sometimes it was on the left, and maybe BC. Here's some possible hypotheses for this situation. Now, this first question might have seemed a little strange, but I'm just curious what you put. It says, how many different possible hypotheses could we make for this situation regarding pre-verbal children and their choice of a toy? Right, so in just looking at those things. What did you say, Raleigh? I'm going to narrow that down to just children will prefer the helper toy. What's another possible hypothesis? They'll prefer the hinderer toy. And what's another possible hypothesis? They don't have a preference, right? Okay. So that's what we're going to kind of clear the air of all these other issues, which are valid concerns, and just focus on these three. Okay. So let's take a look then at part. Well, what did you say for C? If children really do not have a preference, then what would be the most likely outcome? What did you say, Samantha?
I mean,
How many of the 16 will choose the helper toy?
if it probably about half, just
Yeah.
depending on how close, how far they are.
Probably about half. Yeah, it's good. All right, and D, still assuming that infants show no preference. What kind of results would you not be surprised to see when the study is conducted on 16 infants? So even if they don't have a preference, like what would you not be surprised? Even if, say, they didn't choose 8. Say that there weren't just 8 of them that chose the helper toy, right? But something else happened. What wouldn't be surprising? What did you all say? Christina, for this one, did you get to this question?
50%, but I mean, it could go even.
So if you had 16 kids and they all chose the helper toy, and if we assume that they don't have a preference, would that be surprising to you?
60.
Okay. All right, so we've got an issue that there's 16. So let's just look at these 16. If these 16, all 16 of them chose the helper toy, would that be surprising? Just for these 16. So a number of people are saying yes, and a number of people are saying no. So how likely is it then that would happen? If they don't have a preference, then what's the likelihood they'll choose the helper toy? 50-50, right? So if you have a 50-50 situation, how likely is it for you to get all of one and none of the other in 16 trials? Right? That seems like something we might be able to investigate. What do you think? We could just do what? Flip a coin. So that's what's coming. We're going to do that in just a second. But I want to go ahead and tell you how many. So part E says, the researchers actually found that 14 of the 16 infants in the study selected the helper toy. So I have some questions. If it really is the case that infants show no preference between the helper toy and the hinderer toy, do you find these results of 14 out of 16 surprising? Why or why not? So talk just for a quick 2 minutes in your group. So as you discuss, you may want to read that question really carefully before you discuss, because it tells you what we're assuming about society in there. So read that question again really carefully. It says we're assuming something. So based on this assumption, then would it be surprising? Not based on what you think reality is, but based on this particular assumption, and it gives you the assumption. Read it carefully and then discuss. How many would you expect of the 16?
We had said 50% is what we had said.
Which would mean how many?
8.
8. Right, so we'd expect 8. We got 14. So here's the deal. Oftentimes what you expect and what you get are different. So if there's a difference, that means there's some variability, right? So there's variability between what we got and what we expected. So the question is, can we explain that variability in some way, right? Some statisticians would say actually that explaining variability might be what statistics is all about. So we're going to investigate this a little bit today and then continue to investigate it all semester. Is how do we make sense of variability that exists in data? So let's investigate this. Let's go ahead and do it with coin flips. Do y'all have 4 coins in your group? A key question is, how surprising is the observed result under the assumptions that the infants have no real preference for the helper toy or the hinderer toy? So we have to assume this preference. I know this group was saying, well, I think society instills morals in children at a young age, but are we assuming that in this scenario?
Yes.
Well, we're not right now, actually. So even though we might think that it's true, we're not assuming it. We're assuming what?
No preference.
We're assuming no preference. So it says, how surprising is the observed result under the assumption that infants have no real preference for the helper or the hinderer toy? We will call this assumption of no genuine preference the what?
No.
The null hypothesis. Has anyone ever? Let's simulate this situation using coin flips. If children truly have no preference, they will have a 50-50 chance of picking the helper toy. So this was actually proposed by one of the students in the class. So flip a coin 16 times. So each coin flip is going to be a child choosing. And a heads, it says, if heads represents the child choosing the helper toy, count how many of your 16 hypothetical infants choose the helper toy, and then place that blank in the blank on the left. So you're going to do what? Flip this 16 times and count how many heads, and put that number on the blank. Then you're going to do it again, another 16 times, count how many heads, put that in the middle blank, and then do it one more time. 16 times, and put how many heads for the final group of 16 in the last one. Okay, y'all ready? I bet you can do it in under 5 minutes. You come on up. You know your three? Got it memorized? So here's what I want you all to do after you have your three numbers is, tell me your name.
John.
John. So what's your first number, John?
8.
8. So John's going to put a dot right above 8 on the number line. Yeah, make it kind of, yeah, so people can see it. And then what was your other number? 8. So do it close to it, though. Put right above it. Okay, and then what was your other number?
10.
10. And start the 10 line. Okay, so that's what I would like for everyone to do. So if somebody already has your number, just go ahead and put a dot above your number, close to it. Yes? Yeah, so go ahead and just come on up if you already have your 3. And multiple people can put their dots in if you can squeeze in. Don't be shy. So there's a question for H for everyone to look at. This is what the entire class got. Can everyone see this? First of all, does anyone know the name of this? Now, you all have a bunch of data on your papers. Actually, we don't have the data set in one place, like the list of numbers. But if we put everybody's 3 numbers together on a big long list, we'd have a big long list of numbers, and that would be a data set. And now we have a representation of our data set right here. So this is a representation. Look at this, representation. Student demonstrates written evidence. So here, we've met the standard. What kind of, this representation has a name? Do you know what it is? Anybody? So, perhaps a scatter plot. What do scatter plots have? Dots. Okay. Were you going to say something else? Were you going to say scatter plot? Oh, it says dot plot. Oh. It's called a dot plot. Now, what's the difference between a dot plot and a scatter plot? Does anyone? So I'm seeing some of this, right? So there's an x-axis and a y-axis, so that you have two, how many, So for a scatter plot, you have 2 variables, the x variable and the y variable, and you're looking at the relationship between 2 variables. How many variables are we looking at here? I think, what is it that each dot represents? Heads. So 11 means what?
11 heads.
We got 11 heads, right? So you're counting the number of heads when you flip a coin 16 times.
Then there's no extremes, so it is surprising that they would get 14 if there's no preference.
Okay. Okay. How many people agreed with Wade's group that said it was surprising that the people's groups? Let me see those hands. That you're saying that what was surprising?
That they got 14.
Yeah.
That the researchers got 14. That's surprising. Based on this.
Yeah.
How many people agreed? Okay. So some people who didn't agree. Let's have this group talk. Just someone from this group. Go ahead.
It's more that it's improbable than it's impossible.
Okay.
So if you have a 50-50 chance each time, it is possible that all 16 of them could choose one without a preference, but it's just not something that you would expect. So knowing, I don't know how you could be surprised if you know that at the same time, but it still kind of is if it was all one way or the other. Because, I mean, we got 13 right there, and we got 4. So it's, yeah, I mean, it's possible. It just doesn't seem probable. It's not likely.
Okay. So are you saying that it's surprising that the researchers got what they got or not?
No,
It's not surprising.
no.
Okay, it's not surprising. How many dots do we have up here? Did anyone compute that?
23.
There are 23 people.
There's 23 people.
23 times 3. What's that? 69. So out of 69 trials, did we get what the researchers got? Okay. You want to do it some more times? No, nobody wants to. But if we have technology that could do it for us, then that might be nice. So let's let the technology do the coin flips. So let's see. If only I had a helper hinder exploration. Oh, look at this. Here it is. So I'm going to run this. How many times do you want to? How many times do you want to do the 16 flip thing? 1,000 times. Let's do it 1,000 times, and we'll see how many times you got 14 or more. So we'll even let them get 15 or 16 and count it as. All right. So let's do it 1,000 times. So 1,000. All right. So here's our dot plot of 1,000 times. How many times did they get 14 or more? 1. This is counting how many 14, 15, or 16s there are. It only happened once. Once out of 1,000. You want to do it another 1,000? It happened once. Maybe the technology is broken. It happened twice there. Okay, so it actually did it 1,000 times. So, 4 times when you do it 1,000 times. So how likely is that? Not very likely? How should we think? Talk in your groups about how we can think about how likely it is. What do you do mathematically to figure out whether or not something's likely, and how do you make a decision when you say, yes, that's likely, or no, that's not likely? Have a quick minute conversation about that. Go. All right, so let's go ahead and report out. What were you doing mathematically to decide about surprising, and how are you thinking about that? Yazid, what'd you say? Yazid's group, they were talking about it in terms of a curve, and so they were thinking about this way. It's kind of just making a bell curve situation. So, but sometimes this happens, but this isn't what we have. This is what we have. So, all right. How did you make it? So they represented it graphically. Did anyone do talk about what would be surprising numerically? This group was talking about it.
We were talking about fractions.
Uh-huh. And what was the fraction here? Why was it so unlikely?
It's 4 over 1,000.
Okay. 4 over 1,000? And then you even represented it
And then as a decimal.
as a decimal, which is
0.0004.
0.0004. And then I also heard the P word. Percentage was, what was the percentage? 0.4% chance of it happening. So,
1,000, not.
yeah. So this was, well, yeah, so this is 4 out of 1,000. 0.4%. So is that very likely? No. What, did anyone have a discussion about what would be likely? Why is that so unlikely? What if it was 1%? Would that be very likely? 1% chance? 2%? 3%? Did anybody have this discussion? Or you just said 0.4%. That's really unlikely. But what would be likely? I don't know. That's something to think about. We'll come back to that, okay? All right. So let's go to the place where it talks about variability. There's variability between what we expected to happen, assuming the null hypothesis is true, which was 8, and the actual results. This is what I referred to earlier. You beat me to the punch. The question is, can the random process of choosing explain this variability, or is there another explanation? Many statisticians say that the field of statistics is primarily about explaining variability. This is what we are attempting to do in this investigation. We'll continue this throughout the term. So I would like for you, we have just a little bit more time for this activity, to read the terminology here. It introduces 3 terms: probability, p-value, and statistically significant. I'd like for you to read those quick definitions and then answer part J. And as a group, I would like for you to, it says, part J says, based on the above simulations, what conclusion should the researchers draw in this situation? Justify your conclusions using the above terminology. So those terms, those 3 bolded words. Go ahead, each group should write something out really nice, a nice conclusion, so that we could share it with the group, okay? And then I'll randomly call on a group to share. Really, we've talked a little bit about right and wrong answers. I think in some senses, right and wrong is something that will just come out. It doesn't really matter when you're sharing your work sometimes. And it's almost like every question is right and wrong in its own way. And getting it out there and talking about it is what helps us think more clearly. So everything you share in the group is valuable. So anyway. Every single time.
Statistical significance provides probability ensuing the p-value is higher than the null.
Okay. So what did you mean by that? What did your group mean by that?
We meant that within the statistical significance, or statistically significant, it says provides evidence against the null, which our p-value was doing because it was higher than the null, so it was providing evidence against it.
Okay. So the p-value provided evidence against the null. First of all, would you all agree with that? Okay, I see a lot of head nods. So that the p-value, why did the p-value provide evidence against the null?
Because it was higher.
Was it high? How big was it?
It was a 14 instead of an 8. And all the 8.
Okay. So this is good. So what is the p-value here? Let's get this thing straight. So is the p-value the 14? So the actual results, the p-value is related to the actual results. So what are you thinking? Let me see. Yeah, go ahead. Okay. So that the p-value is the 0.04%, or it's not 0.04%, is it? What was it? It's neither one. It wasn't 0.04 and it wasn't 0.04%. It was something else. It was 0.004 or 0.4%. Both of us were putting the point in the wrong spot. So that's the p-value. How many agree with that? That it's 0.4% is the p-value. I'll give you a chance because yeah, that's fine. You're up next. So that if the p-value is 0.4%, then what's the case about the p-value? Is it big? It's lower. It's small. And higher than the null. So
Okay, so the p is the percent. The
Okay.
p-value is the percent.
the p-value is the percentage. So let's see what.
We're saying?
Yeah, I think so.
Okay.
So this is a nice try. This was a good place to get started. Let's see what this other group said. As the wait. Go ahead, Jackie.
P-value is 0.4%, which is really low, and I think it indicates the results we got statistically.
See if I get the right button here. One more time. As the p-value is 0.4%, by the way, it's low. It's even down here low. It's lower than everything else. It means the result is statistically significant. How many would agree with that? I see a lot of head nods. People saying, mm-hmm. Okay. Christina, thank you. Go ahead.
Oh, well, so the p-value is low because it's higher than the null, even though the p-value is percentage, but it's higher because it's 14 out of 16 as opposed to 8 out of 16.
Okay.
It's kind of nice.
Yeah. So this first thing, should we be comparing the p-value to the null? So here's the question. And what is the null anyway?
No preference.
So, so the null hypothesis was that there was no preference. And that means that you would expect to get a percentage of 50%. And we got instead, did we get 0.4 instead? What did we get?
No.
So that's interesting. What did we get? What was the percentage that they got? I don't think we've said it yet. What percentage did they get? They expected to get 50%.
They got 87.
How did you find that? 14 out of 16.
They got 88%.
Yeah, 87.5%. Yeah. No. So hang in there. So, what's this? Student persists in his or her efforts to understand and solve the problem mathematically. Okay? So this is something, y'all, that people will make it all the way through stats class. And actually, this topic comes up at the end, after midterm, usually. But it's something we can get our minds around from the start. But this is something that whenever you talk about it, over half the class is confused. Because we've got how many percentages going on? We've got the 50%. Now we've got this 87.5%. And then we've got this 0.4%. And then we're like, well, is that a small percent or not a small percent? What would be a small percent? And I was asking, is 2% a small percent? And it's like, stop it with the percents. Right? Okay. And, yeah.
So anything that's not close to 50 is going to be a low p-value because it's away from what you expected, which is something that's against whether it's high or low. The number is high or low, the percentage is high or low. It's in the opposite direction of what you expect. So even though the number is high, it's still a low p-value.
Okay. So I think I followed. It's hard to follow, though. It's hard to talk about mathematics. It really is, and it's easy to get confused. But let me see if I hear you correctly. You're saying you expected 50%, which means you would expect an 8. 8 out of 16. So any number that's, what did you say? Any number that's higher than 50% would?
Well, any number that's away. So whether it's closer to 1 or closer to 16, it's going to be a small p-value.
Okay.
It's anything that's going away from your expected in either direction.
What do y'all think about that? You're expecting 50%. What about 10? Would that have a small p-value? Would it be small? You said if you're all the way towards 16, that's going to be small. We said 14 was a small p-value. And how did we find the 14? It was like how many were, if this were our simulation, what's the p-value? 0, right? 0 out of 69. But if we did it 1,000 times, it was like 0.4%. So what would give you a small p-value? And if it's a low p-value, then the result is statistically significant. So let's continue with this question just for the next, it was like somebody brilliant wrote this activity. Just kidding. I didn't come up with this, actually. It was Rossman Chance. It's the people at the bottom that asked this very next question. It's incredible. If the actual study had instead found 9 of the 16 infants,
Can I take
yeah. Could you pass that over to Jackie? Thanks. Yeah. If the actual study had instead found 9 of the 16 infants chose the helper toy, then that decision, thank you, then what decision, I should have somebody else read, should the researchers make based on that result? Do you have enough information to answer that question? What do you want to do? Flip the coins. We could do that again. Or we could have the computer flip the coins. What do you say we have the computer flip the coins for this? But what do we have to change? If only whoever wrote this activity said, here I was counting 14, 15s, and 16s. Now what do we want to count? 9s, 10s, 9s and ups. So we'll change this to 9. And if whoever did this was, which was me, was good with their calculator, then let's run it 1,000 times and count how many. Okay, so we just ran it 1,000 times and there were 9 or more right here. So how many dots are 9 or more? 388. And what is that 38.8% called? It's the p-value in this situation, right? And so what do you think? So I'll let you in your groups answer part whatever we're on, K. So in your groups, come up with a statement and write out part K. See what you can do. I know there are too many percentages in the air, but see what you can do.
0.38 p-value is less statistically significant because it's closer to the null 0.5, but the study needs to be continued more times. So as you continue to do the study, you're going to get closer to 0.5.
Okay. So what do y'all think about that? This is interesting. Do you agree? So the p-value is less statistically significant because it's closer to the null, which is 0.5, but the study needs to be continued more times. Okay. So what do you think? Why were y'all thinking what would happen if the study was continued more times? Can we do 5? Okay, let's see. It might still freeze. We're at 38% right now, or 39-ish. Okay, look. It's not blinking. Okay. If it went to 0.5, what would that mean in this case? Where is this 20% coming from? Can someone tell me where this 20% is coming from? Yeah, go ahead, John.
Well, each time you do it, yeah, you're adding more 9 and ups in there, but you're adding all the others with it. So the more times you do it after a certain point, it's gonna lower your chances. So
if you decrease the number,
yeah,
the p-value would be higher.
If you decrease what number?
The testing number, like if you decreased it to 500, I think it would be, the p-value would be closer to 0.5.
Okay, so let's decrease it to 500. Oh, it went up from 20% to 40%. So maybe if we do it 100 times.
So is your bell curve kind of flatten out?
45%. So what's happening here? That was just fluke that it keeps. Or was it just fluke? We better do it a couple more times for 100. Who am I to say? Everybody's saying their stuff. Okay, here we're 30,
that's 0.49.
32, 46. Oh, did we get a 49?
Yeah.
Yeah.
4.8.
See? It looks like it's 30s and 40s, but what's happening here? What's it counting?
38
Yeah, 38 over 100, but where's it getting the 38? 9 and up. Is 9 and up ever going to, would you ever expect that to be half? You expect half to be what and up? Maybe 8 and up. Or maybe 8, and maybe that'd be more than 50%. I don't know, but 8.5 and up or something, I don't know. But because this is where the majority is going to fall, right in the middle, right? So would you expect this to be whatever the null percentage is? Ever? What are we comparing it to decide whether or not it's statistically significant? We said we had statistically significant results, Jackie, when the p-value was what? Low. All right, so whenever it's low, it's statistically significant. What's the probability that you would get 6 or more? Look like about 80% maybe. So can your p-value even be bigger than the 50% in the null? So do we need to compare the p-value to the null percentage, that 50% that's in the null? I don't know. What are we comparing the p-value against? We said if the p-value was what? Low, right? Then you have statistically significant results. Having a low p-value means the results were surprising, assuming that the null hypothesis were true. So what's surprising? What did you say, Jackie? You didn't expect it, yeah. So if something happened, there was a 0.4% chance. That's pretty surprising. I didn't expect that. What would you expect?
The probability.
Okay. Let's see what some other groups said. Point zero, yeah, what are we comparing the p-value to? The 0.04 was small.
Yeah, but small relation to what?
Right. Did everyone hear? Small in relation to what? Because we said small meant that it was surprising, Jackie said. So what, we got something that only had a 0.4% chance of happening. So what would be surprising for you? If something had a 0.4% chance of happening and it happened, is that surprising? Yeah. If something had a 50% chance of happening and it happened, would that be surprising? Like if you flipped a coin and got heads, wait a second, that's not supposed to happen. So what's the likelihood, what percentage is it going to take for it to be surprising? What do you think? If there's a 100% chance that something would happen and it happened, would you be surprised?
Wait, if it's 100%, does that make it a chance or a guarantee?
What do you think? What do you think? So if you have a 100% chance of something happening and it happens, is that surprising? No. It's a guarantee. What do you think? Is it a guarantee if I say there's a 100% chance that you will breathe in the next 15 minutes? Would you be surprised if you took a breath? No. So what would be surprising? If it's low, what's low?
0%.
0%. If there's a 0% chance of something happening and it happened, would you be surprised? Very, because 0% chance means it can't happen. Yeah, so it won't happen. So I'd be really surprised. Right, that's what I'm asking.
But we experience that all the time with the weather.
Yeah.
100% chance of rain in the forecast,
And-
and it's a monsoon.
Yeah. Does that happen a lot?
Yeah.
A lot? In Tennessee. What's surprising? So you're surprised. If there's a 5% chance of rain and it rained, would you be surprised?
Yes, on either.
Okay. Disappointed. If there's a 10% chance of rain and it rains, would you be surprised? Would you be as surprised as you were if there was a 5% chance of rain? 20% chance of rain and it rains, would you be surprised?
A little bit.
Maybe just a little bit. Where do you want to draw the line? 20%? Anybody want to draw it at 20%? If 20% of the kids would have chosen the helper toy, would you have been like, oh, that's surprising?
I would say 30.
Oh, even 30. Okay. Okay. So you guys are easy. What do you want to say?
It's subjective.
It's very,
If you
yeah.
put a number, then it's not, you're not saying, well, this is the way it is. You're saying,
Right.
my opinion is that at
Right.
a certain point,
Right.
this is low or high.
Right.
So it's always going to be
So that's the thing about statistics, is that you can kind of always make an argument. Statistics is much more squishy than mathematics. Okay, so some people say thank God, and they do really well in stats class when they've struggled in math classes before. Math majors will often struggle with this class because they want it to be. Mm-hmm. It's true. Okay, but I'll just say, all right, so it's 5%. Statisticians kind of as a litmus test say, 5%, then we'll say it's surprising. Because we need to be, you know, kind of.
5% lower? Is that what you're saying?
Yeah.
Okay.
That's the way they use the what?
95% confidence interval.
Okay. So we'll talk about 95. Oh, it was in the pretest, the 95% confidence interval. Okay. So it might be related.